we're wondering, how well does experimental results compare to theoretical results? Let's say that you work at a candy factory and your factory produces candy of different colors. So maybe you have red and blue and yellow and green. And at the factory, you specifically create a specific ratio of certain colors. Maybe all the colors are equally likely. So you say, okay, 25% of the candy we make is going to be red. The other 25% will be yellow. The other 25% will be blue. The other 25% will be green. So in theory, the distribution of the colors should be 25% of each of the four. But then, the candy gets mixed up, it gets bagged, it gets shipped out. And when someone opens up that candy, they may experience a different ratio. So in theory, they should have 25% of each color, equal representation. But in actual practice, in the experiment, if you will, the distribution may be different. And so what we'd like to know is, how good of a fit is the experimental results with the theory? Do they fit each other well? And this is called a chi-squared goodness of fit. And that's what we're looking at. So this word here, chi-squared, this is pronounced like the letter K. So it's not chai or shy like Chicago. It's a hard K sound. This process is going to involve a distribution. It's going to involve a test statistic, a z-score. Well, like a z-score, it's actually a chi-squared score. It's going to involve area under the curve, a p-value. But it's a little bit different than what we've seen before, because we're not working with the normal distribution anymore. So when we look at the goodness of fit, we are checking to see how the experimental results fit the theoretical results. But this is not being done in a normal or binomial distribution. So if you think about the past sections in chapter 8 that we were looking at, we had some problems that were pretty much like yes or no, P's and Q's. That is a binomial distribution. What happens when you have more than just a binomial situation? What if you have a situation where there are many different outcomes, like a Likert scale, where you strongly disagree, you disagree, neutral, agree, or strongly agree? There are 5 options here. These 5 options don't fit well into a binomial distribution, into a yes-no situation. So we have to come up with new statistics. Our overall process is going to be the same, but the formulas that we use will be a little bit different. So we measure this not with a z-score, not with a t-score, but with something called a chi-score. And this is the chi-squared test for goodness of fit. When we put this into hypothesis testing, the null hypothesis is that the observed data, that the experiment is consistent with the theory. Our alternative hypothesis is going to be that they are not consistent. We're going to find a test statistic, a chi-squared value. We are going to compare that to alpha, and we are either going to reject or fail to reject the null hypothesis. You may be familiar with the normal distribution. So if your sample size is close to 50, the area doesn't change that much. Here's 30, 40, 50. There's not that big of a change in area. But when you drop below 30 people in your sample, remember talking about this, why 30? Because the shape of the curve changes when you get below 30, and you can actually see that happening here. The normal distribution changes when you get a sample size below 30. This was the normal distribution. This is the distribution for chi-squared. And chi-squared, this is the distribution, and if you want to see the formula, here's the formula for chi-squared. Now, again, in this class, we are not going to explain where this formula comes from or why it is what it is. You can take an advanced statistics class and understand the derivation of this formula. We're just going to use the formula as a tool so you can visually see what the formula looks like. Now, check this out. Think of a tsunami. The wave is out in the ocean and it's really wide, but it doesn't have a very high crest. As n gets smaller, as your degrees of freedom get smaller, that tsunami approaches the shore and gets larger and larger and larger. This is how chi-squared behaves. It's just like the normal distribution changing shape, except for this is the chi-squared changing shape. So the first thing you have to do is determine what is the shape of chi-squared. And that's based on your degrees of freedom. Once you have your degrees of freedom, you plot your test statistic, and chi-squared is always shaded above the test statistic. You will always be looking for a right-tailed area. So how do we calculate chi-squared? This is our test statistic. It's kind of like the z-score or the t-score. We had the z-score, we had the t-score, now we have chi-squared. This is the formula for calculating the test statistic. For each sample, you take the observed data point, find the difference between that and the expected data point, the theory, square it, and then divide by the theory. And once you have that chi-squared, you will graph this test statistic on this axis. Let's say your degrees of freedom are 4. Let's say chi-squared equals 3.8. So you're going to put a mark at 3.8, and you are going to find the area to the right of the curve at 3.8. So we have talked about binomial distributions. We've talked about normal distributions. Now we're talking about a chi-squared distribution, and look at what the formula is to find that area. It's right here, chi-dist. Chi-dist is the Google Sheet formula to find the p-value, the area above that curve. So that's what we're going to use in our Google Sheet, and it's already built there for you. If this p-value, if we have a threshold, let's say our threshold is 5%, if this p-value comes in above 5%, that's bad for us. That means we fail to reject the null. If this p-value comes in below 5%, that's good for us. That means we get to reject the null and replace it with our alternative hypothesis. So if you were to roll a 6-sided dice 500 times, you would expect to have about 83 ones and 83 twos and 83 threes and 83 fours. So if you rolled it 500 times, you would expect about 83 of each one. So if you actually go out and roll a dice 500 times and record how many ones, how many twos, how many threes, we could compare the theoretical distribution to the experimental distribution. And that's what this table does. This is our experiment. So we went out and we rolled the dice 500 times, and we kept track of how many ones, how many twos, how many threes, how many fours, how many fives, how many sixes. And then this is the theory. So theoretically, if I have a total of 500 rolls, so 500 divided by 6, I should, in theory, have about 83 ones and 83 twos and 83 threes. If this was theoretically a perfectly balanced dice. So what we're going to do is we are going to take the experimental value for the ones and the theoretical value for the ones, and we are going to subtract them. We're going to find the difference between the observed and the theory. Then we're going to square that difference, and then we're going to divide it by the value for the theory. And then we're going to do the same thing for the number 2. We're going to take the experimental, we're going to subtract the theory, get the difference, we're going to square it, and then we're going to divide it by the theory. We're going to do that for each one of these, and then we're going to add them all up. And that is our test statistic. This is chi-squared. You're going to take that chi-squared value and you're going to plug it into chi-dist. And so if we were to graph this, here is our tsunami distribution, and we have a value at 1.5, and chi-dist is going to give us the area above that target. This is the p-value that we're going to use to compare to our threshold. And once we compare it, we're going to either reject or fail to reject the null hypothesis. So here's what everything looks like. This is the graph actually of that distribution. This is our p-value. Right here, you can see this area is huge. This is a huge area. And so we are very much going to fail to reject. So that means that it is a fair dice. There's not enough evidence to show that the dice is not fair. Therefore, it's a fair dice. Our experimental distribution was not significantly different from the theoretical distribution. And so it's a fair dice. There's nothing to lead us to believe that this dice is unfair or that there's anything weird with the distribution. So this is an example where you have everything is equally likely to happen. Okay, every outcome was equally likely. We can also have an experiment where we are giving probabilities for each one. So they're not equally likely. So here is the fruit snack that I was alluding to earlier. And so here you have the expected probability of fruit snacks that are blue, and the probability that they're green, the probability that they're red, and the probability that they're yellow. The factory says 40% of the fruit snacks that we manufacture are blue. We manufacture it that way. Here it is. It's 40%. There's no questioning that. They know exactly how many they make. 10% are green, 25% are red, 25% are yellow. That is the theoretical, right from the factory value. And so we go out and we buy a big bag of fruit snacks, and that bag of fruit snacks has 127 fruit snacks in it. And we count. Of those 120, 36 were blue, 16 were green, 38 were red, and 37 were yellow. So of our 127 fruit snacks in our experiment, this is the distribution that we got. How well does our distribution of blue, green, red, and yellow match up with the factory's theoretical distribution? So if we have 127 fruit snacks and 40% are supposed to be blue, then in theory, we should have about 51 fruit snacks that are blue. Our counting of fruit snacks said we only had 36. Theory says we should have 51. The experiment showed that we only had 36. So this number is a little bit low, but is it significant enough? That's the question. If you take a look at the greens, 10% of our fruit snacks should have been green. 10% of 127 is about 13. We would expect about 13 fruit snacks to be green. When we counted them, we had 16. So here we're a little bit above the expected. In theory, 25% of the 127 should be red. That's about 32. We had 38. And so that's a little bit above. And then for yellow, again, 25% of 127 is 31.75, about 32 fruit snacks. We had 37. And once again, that number is a little bit above. So you can see we were low on the number of blues, but we were up on the greens, yellows, and reds. Is this significant? Let's figure out chi-squared. So once again, you take your experiment. So this is our experimental data. This is the number of fruit snacks when we counted them. This is the theory from the company, taking our 127 and breaking it into those ratios that we talked about earlier that the company had given us. We find the difference between the two. We square that difference, and then we divide it by the theoretical value. We add these all up, and that, my friends, is chi-squared. This is our test statistic. Think of it as your z-score. This is the target that we're going to use in our distribution to find the area above. So here's all the data in a spreadsheet. This is the graph in Desmos. So here is that value right here. This is our target. This is our test statistic, that 7.268. And we are looking for this p-value. What is that area? And that area shakes out to be about 6.4%, 6.4. So our significance level was 5%. Our p-value came in above it, which means we fail to reject the null hypothesis, which tells us that the observed frequencies, the 127 fruit snacks that we opened up and counted, were consistent with the expected frequencies from the factory. It was a good fit at the 5% threshold. So that means that the quality control that measures the colors of the fruit snacks that go into each bag can confirm that the ratio of fruit snack colors is consistent with the manufacturing. So we looked at two examples here. We looked at an example where all events were equally likely, the rolling of the dice where they're all equally likely. And we also looked at an example where each individual outcome had a different ratio, a different percentage. And so this is the 9.1 spreadsheet. And you'll notice that there are two tabs down at the bottom. One tab is when everything's equally likely. The next tab is when there are different given probabilities. In problem number 2, we have goodness of fit. And in this particular case, the 4 outcomes, category A, B, C, and D, all have different probabilities. You can see the probability of A is 10%, probability of B is 10%, probability of C is 30%, and probability of D is 50%. In our spreadsheet, we do not use the first tab. The outcomes have different probabilities, and so we're going to use the second tab. So what I'm going to drop in here, let's delete this old information. I'm going to put in the observed frequencies, 21, 26, 44, 27, and then I'm going to put in the given probabilities. The given probability for category A is 10%. So I'm going to put in 10%. The total number of items that I've sampled is 118. If I take 10% of 118, I would expect to have 11.8 items. I got 21 items in bucket number 1. This is 10%, this is 30%, this is 50%. And here is my experimental results from me counting the results of the experiment. And here is my theoretical results. Then what you want to do is just really quickly take a look at these. I'm expecting 11.8. I got 21. I'm expecting 11.8. I got 26. That's pretty far off. I'm expecting 35. I got 44. That's pretty far off too. I'm expecting 59 and I got 27. Way low. There are some serious red flags with this data. Let's find the difference between the two. So we take our observed and we subtract the expected and we get these values. Here's the difference. We square the difference and then we divide by the expected value, and that is our Pearson residual. And these Pearson residuals are huge. 17, 2, and 7. You got a chi-squared value of 43. And again, to put that in perspective, you are going to have a chi-squared distribution, and out here at 10, 20, 30, 40, 43, that is where your target's going to be, and you're finding this little sliver of area under that tail. And this graph is probably an exaggeration. It's probably more like this. That. That's probably, this is an extremely small area, extremely small value. Yeah, you can see it's 0. Let's kick it out. Let's see how many. There we go. They're 0.0000000174. That is a extremely small area. This means we're going to reject the null that the observed matches the theory, and we're going to say there are some issues with this distribution. So before we do that, let's drop in all these values. Okay, so our expected frequencies, we're just going to copy and paste these values. And then we're going to copy and paste our Pearson residuals. What is the chi-squared value? 43.7. That's funny. P-value, 0. And we are going to reject the null hypothesis. Yes, please. So our value, yeah, this data set is really bad. Yeah, this is where you immediately call in quality control and say something is wrong with your process. You have way too many blue fruit snacks.